Hello, advanced algebra students. I hope that everything is going great. We are doing yet some more notes for chapter 3. This is actually kind of fun. I know this is strange, but I really love factoring. I love finding zeros and learning more about functions. And hopefully you find this somewhat enjoyable yourself. I'm really looking forward to working with you in person on this. So here's the deal. So far in this chapter, we've looked at various different aspects of higher order polynomials. In other words, functions that have a degree higher than 2. We've looked at how to determine their end behavior, how to find their zeros, how to graph them, and how to do various operations with them. What we're going to do today is learn some additional tools for finding all the possible rational zeros, evaluating how many zeros there are, and also identifying zeros that come in pairs. So it's kind of like a bag of miscellaneous tricks related to polynomials. Now, the first theorem we're going to talk about is called the rational root theorem. And it's this really, long sounding theorem. But basically, what it tells us is that all the possible rational solutions of a function have to be in the form of the constant of the function divided by the leading coefficient. So let me give you an example and show you what I mean by that. If our function is 8x to the 5th minus 32x to the 4 plus x squared minus 4, this -4 is our constant, and this 8 is our leading coefficient. The rational root theorem tells me that all of the possible rational zeros, so in other words, not irrational or imaginary, but just rational zeros, all possible rational zeros have to be in the form of either a factor of the constant divided by a factor of the leading coefficient. So in this function, for example, all the factors of the constant are positive and negative 1, positive and negative 2, and positive and negative 4. The factors of the leading coefficient are positive and negative 1, positive and negative 2, positive and negative 4, and positive and negative 8. Notice, for example, that I can tell right here that 3 is not going to be a zero of this function, because there's no way I can take 1 divided by 4, for example, and get 3. So all of the possible rational zeros, if we wanted to look at every possible combination here, we could do 1 divided by 1, 1 divided by 2, right? We could do 1 divided by 4. We could do 1 divided by 8. Now, we could also do 2 divided by 1. 2 divided by 2 I already have here. 2 divided by 4 I already have. And 2 divided by 8 I already have. I could do 4 divided by 1. 4 divided by 2 is already on my list. 4 divided by 4 is on my list, and 4 divided by 8 is on my list. So here's the deal. This sometimes is helpful. To be honest with you, it's not helpful a ton, because all this is doing is narrowing down the list of possible rational zeros, but there's still quite a few here. I mean, it looks like we still have 12 possibilities. So there are some cases where this is more helpful than in others, and we typically are not really going to use this theorem that much, but it can in some cases be helpful. So I kind of list it kind of just as an extra little tip. So let's do an example of using a real world problem to find some zeros. A jewelry box in the shape of a rectangular prism measures 2x plus 1 inches long, 2x minus 5 inches wide, and x inches tall. What are the dimensions of the jewelry box in inches if the volume is 21? So again, remember that when we're talking about a prism, the volume is length times width times height. And we are told here that the measurements are 2x plus 1, 2x minus 5, and x. I would probably FOIL this here. So 2x times 2x would give me 4x squared. 2x times negative 5 would be negative 10x, and then I have a positive 2, so it'd be negative 8x when I combine my like terms, and a negative 5. If I take x times everything, and I think I'm going to put this on the left, I'm going to get 4x cubed minus 8x squared minus 5x. And then when I subtract the 21, 4x cubed minus 8x squared minus 5x minus 21 equals 0. So, you know, there are so many possible rational roots here because we have to look at all the factors of 21 divided by all the factors of 4. So there are quite a few. To be honest with you, what I would do is put this on a graphing calculator, and I would see that the graph appears to cross the x-axis when x is 3. Notice that this would work because 3 is a factor of 21 and 1 is a factor of 4. So this does work out as 3 divided by 1 as being one of the possible factors. So I typically use the graphing calculator to find my first 0. Now that we know that 3 is one of our zeros, we can use synthetic like we talked about in the last lesson to continue to factor this. So let's look at this function right here, and we're going to bring our coefficients over here. 4, negative 8, negative 5, and negative 21. Again, I plug this into the graphing calculator to see that 3 appeared to be one of my zeros. I'm bringing down the 4 here. And the good news is that 3 does work. I can see that the remainder is 0. So I know that my function can be written as x minus 3 times my other factor here. 4x squared plus 4x plus 7. Now that polynomial is not factorable, but I can use the quadratic formula. So in terms of finding roots here, I know that I would have this root, x minus 3 does give me 3 as a possible answer. If I wanted to see if there were any additional rational roots or other roots at all, I could use the quadratic formula. Negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. This ends up being negative 96 here and 8. But at this point, I don't need to go any further because this was a word problem that was asking us to find the dimensions of a jewelry box. Because this is a negative number here, it is going to be an imaginary solution. It is possible that I might have done this and found an irrational solution, which would be something I could use in the real world, but an imaginary solution is something I cannot. So I'm only going to end up using that example right there. Okay. So this, again, is just kind of like a little mixed bag in the notes today about a few different theorems that can be helpful when we're looking at polynomials. Another thing that we can learn is the fundamental theorem of algebra basically tells us that the degree of the polynomial tells us the maximum number of zeros. So for example, if it's fourth degree, there are going to be at most 4 roots. If it's third degree, there are going to be at most 3 roots. If it's second degree, at most 2 roots, and first degree, at most 1 root. Okay, I'm just trying to think if we need to do an example of this. I really don't think that we need to. I think that we're probably good there. I think what I would like to do is jump to something called, because we've done examples, quite a few of those, where you've seen that the degree of the function tells you the maximum number of roots. Let's go ahead and look at the conjugate root theorem. And we'll do one example of that, and then I think we'll be good for these notes. So the conjugate root theorem tells us, let P be a polynomial function with rational coefficients and let A and B be real numbers. Then if A plus the square root of B is a root of that function, then A minus B is also a root. Similarly, if A plus BI is a root, then A minus BI is a root. So what this is telling us in essence is that some kind of roots come in pairs. So irrational roots come in pairs and imaginary roots come in pairs. So let's do an example here. I believe this would be example number 3. What is a quadratic function P with rational coefficients in standard form such that it has 2 plus 5i as a root? Well, I know from what we just talked about that if 2 plus 5i is a root, then it must be the case that 2 minus 5i is also a root. I also know that if these are roots, they represent how I can factor the function. So I know I can take x minus that first root times x minus the second one. Now this can be a little bit confusing to the eyes, but remember, let's just do a little side example here. If I have something like x squared plus 7x plus 12, right? And this is factored as x plus 3 times x plus 4, and I set it equal to 0, I'm getting factors of x. X is negative 3 and x is negative 4. So if I told you that negative 3 was a root, you would know that x plus 3 was a factor. I'm just doing the same thing here. All right, let's go ahead and talk about how we can simplify this, because this is not that straightforward, and I do think there are some in the homework like it. What I like to do on these, we're trying to work backwards in this case. So we're looking at the factored form of the equation, and we're trying to FOIL it back out. I would distribute this minus sign in front of the parentheses here, and this minus sign as well. If I do this, I'm going to get x minus 2 minus 5i here, and then x minus 2 plus 5i here. This is kind of cool how this ends up working out. In terms of doing the multiplication, it can be helpful to see this now as in the first parentheses, x minus 2 minus 5i, and just kind of grouping the x minus 2s. This is like a little organizational skill here. Now let's go ahead and FOIL. Here I'm taking x minus 2 times x minus 2, which is x minus 2 squared. Here I'm going to take 5i times x minus 2. Here I'm going to take negative 5i times x minus 2. And on the end, I'm going to be taking negative times positive, so this will be negative 25i squared. Now I think this is kind of cool. If we look at these two terms right here, they all cancel out. This is positive 5i times x minus 2. That is negative 5i times x minus 2. Those are going to cancel out completely. Also, keep in mind that I squared is equivalent to negative 1. Now, I do need to FOIL this x minus 2. So that's going to be x squared minus 2x minus 2x. And then negative 2 times negative 2 is positive 4. Here I have negative 25 times negative 1 is positive 25. So I've got x squared minus 4x plus 29. This function right here would have 2 plus 5i and 2 minus 5i as its roots. All right, I know that was kind of a difficult example. We will do more together in class. So thanks so much, you guys, and have a good night. Bye.